Good morning. My name is Carme Belarte and I am presenting the experimental works that have been carried out within the project Transdisciplinary and Experimental Study of Combustion Structures in the Western Mediterranean during Protohistory, the TRANSCOMB project. This project is led by the Catalan Institute of Classical Archaeology, the ICAC, and is funded by the Spanish Ministry of Science and Innovation. It counts with the participation of about 20 researchers from different Spanish and French institutions and also with the collaboration of the Ciudad Iberica de Calafell archaeological site in Tarragona, Spain. The goal of this research is to improve our knowledge on the combustion structures in the northwestern Mediterranean during the first millennium BC, focusing on the northeastern Iberian Peninsula, the south of France, and the Balearic Islands. In this context, Iron Age settlements were agglomerated sites. Houses were usually distributed sharing party walls and built against a perimeter wall, often a defensive rampart, as in the example of Calafell. In these settlements, predominant building materials were stone, earth, wood, and herbaceous plants, as we can see in these images. As for combustion structures, hearths and ovens, these can be located inside or outside buildings and in different positions inside rooms. Hearths can be of different morphologies. Their plans are mainly oval or rectangular. Some consist of an earthen surface built directly on the floor, whilst others are semi-excavated in a shallow pit, sometimes with a preparation layer of pottery sherds, pebbles, or also both types of materials. Some of them are delimited by an earthen border. The preparation layer is supposed to improve the efficiency of the hearths, allowing them to reach higher temperatures or keep the heat for a longer period. Other variables, such as their location or the fuels used, must have played an important role in this respect. To date, for the study Iberian period, these installations have been mostly studied from a typological approach, and the use of other methods of study are still scarce. Within our project, an interdisciplinary methodology has been applied in order to analyze different aspects such as construction techniques, fuels, or uses of these structures. This methodology includes anthracological analysis, study of phytoliths and calcitic microremains, Fourier transform infrared spectroscopy, thin section micromorphology, organic chemistry, and experimental archaeology, which is the focus of this presentation. Interdisciplinary analysis have first been applied to archaeological hearths and ovens from the area and period, and later to experimental hearths and ovens. The experimental works have been carried out at the Ciudad Iberica de Calafell in Tarragona, Spain. This is a reconstructed Iron Age site, open to visitors and to educational activities, and is also an experimental archaeology center and EXARC member. The experimental archaeology program concerns experimenting with replicas of Iron Age fire installations for comparative purposes. The first step was the construction of 6 experimental hearths and an oven, whose locations are shown on this plan on the right. Experimental combustion structures were of different types and locations and based on archaeological data. One of the hearths was built outdoors within a shallow pit filled with earth mixed with water and without a preparation layer under the combustion surface. We can see the construction process here. A second outdoor hearth was directly built on the floor, also without a preparation layer. The third hearth was built indoors in a shallow pit and with a preparation layer of pebbles under the combustion surface. Another indoor hearth, also built in a shallow pit, had a preparation layer of pottery sherds under the combustion surface and was delimited by a border made of earth mixed with straw. The fifth hearth, also indoors, had a thick mud border and mud brick inside, composing an elevated platform covered by mud mortar. The last indoor hearth had 2 successive preparation layers, one of pebbles and one of sherds, and was also limited by an earthen border. Finally, an oven was built outdoors with adobes covered with mud and with 2 openings, the frontal oven door and a second one on the top. Once these structures were completely dried, a new part of the experimental project consisted in the repeated lighting and use of all of them. The main aim was to obtain data about the efficiency of these structures, their uses and the fuels employed. We have conducted 3 fire testing periods of these structures with different weather conditions. Each of these periods lasted 5 days. During the testing periods, we repeated the firing of the structures as many times as possible in order to compare the duration of the fire and the temperatures reached with the different fuels in different kinds of structures and locations. All the structures were sampled for interdisciplinary analysis. We used various fuel types: oak and pine wood, pine cone, barley straw and weeds, wild grasses and palm leaves, in addition to sheep and cow dung, according to the available archaeobotanical records, wood charcoal and plant and fecal microfossils. For each combustion, the total amount of each fuel material was weighted with an accurate kitchen scale. Experimental fire installations were sampled for interdisciplinary studies using the same methodology that had been applied to archaeological structures. Before lighting the hearth, samples of the earth layer were recovered in all cases. To light the fire, we used present-day matches, as the study of techniques of making fire of Iron Age societies was not an aim of the project. For all the fires, we recorded time and temperature measurements elapsing between the initial fire lighting and the end of combustions. To do this, we used 2 different types of portable pyrometers, K-type pyrometers and infrared pyrometers. We used the K-type thermocouple pyrometers with a detector placed within the burning fuel to measure the temperature of the combustion surface. These devices automatically record the temperatures at predetermined regular intervals. They remained under the fuel until the fire was extinguished. And infrared pyrometers were used to measure specific points of the flames and later to the embers, looking for the highest temperature. And also to measure the temperature of the oven walls, the surface of ceramic pot and lids, and of the contents. During the combustions, we boiled water as well as different products in replicas of handmade Iron Age cooking pottery. These practices allowed us to know which was the minimum temperature needed on the combustion surface for the water to boil and to keep it boiling for a certain number of hours. Most of the structures have been submitted to several complete combustions, changing the fuels employed from one to another and alternating wood with dung, as in this example. After each combustion, new samplings have been conducted. The fuel remains, both ashes and charcoal, in addition to partially burned plant and dung remains, have been collected for integrated macrobotanical and microfossil analysis. Also, we conducted systematic collection of samples for infrared spectroscopy and biochemistry, following the specific protocol needed for each analysis. Then, we extracted blocks for thin section micromorphology. Finally, one of the hearths have been partially excavated in order to better appreciate the thermal alterations of the sediments. As a result of these works, we have obtained a huge amount of data. Some of the analyses are still ongoing, and we can only present some preliminary results or considerations and can guide future research and allow to better interpret the archaeological data and taphonomical issues. All the structures have turned out to be functionally efficient, with independence of the construction technique, the fuel type and the location. Hearths of different typology and with different locations can maintain a pot with boiling water and food in it for a long period, at least 6 hours. In this example, we lit the fire about 9:15 am and placed a pot on the hearth a few minutes later. We had some difficulties to keep the temperature rising and needed to add fuel an hour later, indicated with a grey arrow. The water boiled at about 11. We then added pork bones and they kept boiling till 5 p.m., so during 6 hours. Thermal alterations in the surface of all the structures were already visible after the first combustion, and their central area became reddish or grey-black. After each combustion, these changes of color of the earth and fire surface were more visible. Location of the hearths and the air circulation are key points in fire lighting and management. In indoor hearths, the existence of an aperture such as a small window over the fire can function as a kind of chimney and help to evacuate the smoke. However, a side aperture such as an open door may provoke an increasing of the smoke inside the room. In this example, just after the lighting, the room was filled with smoke, but it concentrated on the top part of the room, next to the ceiling, and then quickly started to leave through the window. After a few minutes, there was no smoke inside. It is important to mention that animal dung has excellent properties as a fuel source, since it burns for longer than wood when dried. However, the climatic conditions, especially humidity, clearly affect dung properties as fuel. The results of burning dung in May or June or in November have been different in terms of temperature reached or stability of fires, as in November the weather was rainy during the experimental works. Still concerning dung, during the experimental works in November, we could compare the behavior of the same hearth and indoor structure using wood and dung. The graph on the left shows a combustion where we boiled pork bones for 6 hours using wood as fuel. The graph on the right reflects the behavior of the same hearth using dung and shows a very different situation with a less stable fire. The fire surface, orange line, was most of the time under 300 Celsius degrees compared to 600 or even 700 on the left. And we did not succeed to keep water boiling for a time long enough to cook bones. In general, maximum temperatures reached in all the structures were lower in November. This was also noticeable in the case of the oven. Also, in November, outdoor hearths did not keep the temperature for as long as indoor structures using the same fuel type, as we can observe on these graphs, where we show the behavior of an indoor and an outdoor hearth fired with similar fuel, both in November. We arrive now to the conclusions. The different interdisciplinary analysis of the experimental hearth and oven are still in progress. Comparison of their results with those coming from archaeological structures will contribute to a better knowledge of the functioning of the archaeological installations. Systematic records from experimental combustions, as conceived and applied within this project, are needed to deepen the knowledge of construction, use and maintenance of combustion structures, the fuel management and use, and the activities related to fire installations. This kind of approach includes a narrow collaboration of archaeologists with different specialties and has no precedence for this area and period. Further experimental combustions are still needed to complete the records and refine the interpretations. Nevertheless, the implementation of this project is in itself a significant achievement. These are the results of a collective and interinstitutional project, and we would not like to finish without showing the names of all the members of the project. We would also like to acknowledge the research team responsible to the archaeological sites where we conducted samplings. And finally, thanks to all these who have been listening.